Dr. Srinivas, thank you very much. Welcome once again, and please go ahead, sir.
Thanks, everyone, for the patience. So let me take a brief moment to, provide a simple scenario of imagination. Assume that we have a pain in the heart and we go to a hospital where there are invisible doctors whom you don't know what their doctor's qualification is, what their doctor's expertise is, but all you know is they are all having the experience of having done hundreds of surgeries. So you go into the room, you are just having the confidence that there are histories of successful hundreds of surgeries by this set of doctors. You don't know what their degrees are they even robots, are they humans, doesn't matter. But will I go and trust my life or surgery to be done on my heart by this group of experienced surgeons? So does it sound scary? The actual scenario of successful AI today, which is based on this whole phenomena of deep learning, is exactly like what I mentioned, that you go into a surgery room where there is a set of surgeons who only confidence you have is they have done successful surgeries, hundreds of them. That's fine. But why they are successful, what is their underlying qualification which makes them successful, which gives us more confidence into the surgery being successful, is not known. So now think about such a scenario. What is the issue with such a scenario? The issue with such a scenario is we are treating our life to a black box, which we know is successful in the past. We rely on the success of the past to be able to get through the surgery to be successful now. So that is exactly the problem which is ailing current AI systems. And that is what we call as black box and AI models which do not have transparency. So today, as we already know, primarily the technology which is used in context of AI is this whole concept of machine learning. And machine learning, as you all know, we are talking about as the most recent advanced set of techniques leveraging data to provide us insights. But there is a big problem in some of the very successful machine learning models. The idea is there is a model which is generated from data, and users are asked to trust such a model to make the decisions, analogous to our experience-driven doctors for our heart surgery, right? So we know that there is a model which is like a doctor who has been successful based on past experience, but very often these models are black boxes. And when you are seeing black boxes, what typically happens is we don't have any clue about the rationale behind why the model is predicting or why the model is giving such an answer. What is the rationale behind the model's prediction? Why we should trust the model output? These are the questions which are asked of the AI models in many domains, especially those which are highly regulated, those which lead to human lives. For example, if you're talking about the medical imaging scenario where there is a X-ray detection for cancer, or let us say we have an insurance risk model which looks at different profiles of the users and predicts some risk and says that, okay, this is the amount you have to pay. Or whenever you're talking about a scenario where you have decided to, detect a certain kind of malfunction in your machine just by looking at the data of the machinery. all of these scenarios, whether it is the machine malfunction, whether it is the detection of malignant tumor, or whether it is a driverless car trying to understand what speed you should go ahead, all of these rely on a model which is typically a deep learning based black box. And in all of this, it is bringing a huge potential problem from a trustworthiness of the end user in these models, because there's a question of life being trusted there. We trust our life to the driverless car. We trust our life to the doctor or the radiologist who is powered by AI in understanding the X-ray. So, is the current models like accuracy and aggregate measures like sensitivity, are they good enough? Are they good enough for neural nets? Are they good enough for deep learning models? So, what we need to also look at is, while from a life-taking perspective, these are challenging, but it's also important to understand that in domains like insurance, in domains like healthcare, regulatory compliance also becomes important. So what does regulatory compliance require? The regulatory compliance requires us to be transparent into the decisions we are making. When I say transparency into the decisions, it's about visibility into the rationale of a decision that is made based on the data. So it is also important to understand that in all of these cases, we need a better model for AI, which is giving us a better visibility into the rationale of the decision making by AI models. And that, my friends, is nothing but explainable AI. There is a school of thought in the deep learning school of thought, especially some very prominent scientists say that explainable AI is bullshit. It's not required. It's basically a bull. It's not required. Why, when a whole deep learning is working, why should we talk about explainability? If it works, if it ain't broken, don't mend it. That's the idea. But you see that important thing here is not about just a working, highly accurate model. It's about being able to explain to a patient if something goes wrong. If some private data gets accidentally goes into the training data and gets leaked, or if due to malfunction of the brake or malfunction of the driverless car, you have a life which is lost because of the fault functioning of the driverless car, who will you hold responsible? Why will you hold the model responsible? What is the reason why the model took that decision? So these are the scenarios where explainable AI is very, very crucial in modern applications on AI, especially in sensitive domains like insurance, healthcare, financial services, etc. So now coming to explainable AI tools and approaches. There are several tools and approaches which are very, very common in today's world. One of the first set of algorithms and techniques which are useful in rendering explainability is just keep it simple. The principle of keep it simple and safe for the user keeps handy here. Means I don't want to get into complex black box, unexplainable, complex ensemble models, which are quite maybe certain degrees of accuracy more accurate than some of the simpler models. But if my model is simple but can give me a good visibility into the rationale of the decision which I have taken, it is a good starting point into explainable AI. So what you do is you try to compromise explainability versus accuracy. But at the same time, does not mean that these algorithms are not so accurate. They are reasonably accurate. Maybe some 5%, 10% you may get extra by deep learning. So those kind of explainable algorithms like decision trees, linear regression, or in fact, there are some similar concepts called as rule-based systems, which can be extracted from data using machine learning. So these kind of systems, while they are simplistic and maybe of slightly lower accuracy than deep learning models, but the beauty is they can really give insight into why the algorithm gave such a decision. For example, let's take a simple idea of linear regression. Linear regression, as you all know, is about explaining an output y in terms of multiple inputs x1, x2, xn. So if you know that y equal to m1 x1 plus m2 x2 plus mn xn plus c, if m is high for some particular variable xi, mi, then mi is definitely indicating that the relative contribution of xi is higher compared to other x's. Same way, the sign of mi makes a difference. Like if it is positive, it means it's positively influencing the output. If it is negative, it means it's negatively correlated with the output. So you get better explainability of the influence of this particular input variable xi on the y. Slightly more complex is decision tree. As you all know, what is a decision tree? Decision tree is nothing but it is a model where at the top level you take a domain, take a domain variable, let's say age. You say age is less than 50, age is greater than 50, 2 branches. Then age is less than 50, you go in that branch, the next time you say, okay, salary is less than 10,000, salary is greater than 10,000. Then you say habit, has a habit of traveling, not so traveling. Then finally, what you want to do is predict possibility of getting, COVID. That's probably the classification problem you're looking at. So at the leaf node, you will have probability. Is he going to get COVID? Not going to get COVID. So if you see, if you reach a leaf node where you're seeing that you have reached a probability of getting COVID and the branch has come through, let us say age is greater than 50, and let us say he has a lot of travel in his work, then he goes into the leaf node where it says he will get COVID. So what is happening? There is a proper assignment of attribution of input conditions leading to the final decision of why somebody is probably considered as he's a probable candidate for COVID. Whereas somebody like, say, you go into a path where you say age is less than 50, then go to not traveling much, then probably not catching COVID. So this is becoming an attribution of the conditions which are leading to the leaf node of the condition of the output. So what you're talking about is there's a proper rationale to the output in terms of the input, and that is what is giving you the benefit of explainability via the simplicity of the algorithm itself. Then comes the important other categories of algorithms called as ensemble algorithms like random forest, which are slightly complex because they have hundreds of trees together. But they give one big interesting thing, which is what is known as variable importance or feature importance, which actually highlights what is the relative contribution of each of the input variable to the output decision. So in that sense, we can find out that probably top 6 variables are contributing to 99% of the decision. Others are very, very small, 0.01, etc. So you know out of the input features, which of them are kind of contributing maximum to the precise notion of what is called as the output as dictated by the input variables. So you may as well ignore some of the remaining insignificant features or input variables. The next one, line, I'll come to a bit later, but all the other ones, activation maps, class activation maps, gradient class activation maps, saliency maps, deconvolutions, these all come under a separate category of applications of explainability known as white box methods. White box methods means you need to understand the internals of the neural network, which has actually gone ahead and given you the actual decision on the particular image. So these techniques, they reverse engineer the architecture called convolution neural networks and get you the idea of what is the part of the image which is primarily responsible for this decision. So for example, if you have an image of, say, the lungs x-rays, so it will show a certain point of the x-ray which is primarily responsible for the decision that the CNN has flagged it as potentially COVID. It could be a specific marker which are responsible for that. So the beauty of such kind of models is they give precise explainability for really conventional techniques which do not have that, but these guys exploit the structure of the internal machine learning neural network to reverse engineer and work on getting to the pinpointed part of the input which is responsible for the actual decision. So we have 4 categories as we've seen: explainable algorithms, feature importance, then white box methods. But then the most common approach is what we call as line, which is a black box method. The idea of black box method is very simple. I don't care about what your neural network model is or what your model is. Is it a tree? Is it an ensemble? Is it a support vector machine? Or is it a logistic regression? Or is it a CNN? Or is it an RNN? Or is it simple multi-layer perceptron? Doesn't matter. But the idea is, I will use the concepts from conventional testing, known as mutation testing, to provide a black box interpretation of the relation between input and the output. So the idea is, we try to use something which is model agnostic. What is model agnostic? Model agnostic means it does not look into the model. Like the previous case, we looked at deconvolution and convolution maps, which are basically looking at the actual structure of CNN and reverse engineering. But here we take that whole thing as a black box. Second thing is, it is very, very much dependent upon a black box approach, which is model agnostic. The second part is locally interpretable. Locally interpretable is very important from the perspective of understanding the concept of what is known as mutation testing. In conventional testing, mutation testing is a very popular technique to test for deriving bugs or deriving incomplete coverage, etc. What the mutation testing does is it takes an existing solution and perturbs the input slightly around the existing input and tries to find out how the reaction of the program is to these perturbations of the data. The line also does exactly the same thing. What it does is it tries to explain the result of a classifier, it may be image classifier or a text classifier, so that for an individual prediction you can find out what has been the part of the original data which is responsible for that prediction. It's very much similar in that sense to what a GradCam like white box method would do, but the approach they take is slightly different. The way they look at is they try to look at creating this kind of a mapping by feeding variations of your data into the machine learning model. So what it does is it takes your current working classifier, creates zones within that, small different zones, which is what we call as superpixels, and then within that we try to create variations of the data within each superpixel and see the effect of that on the prediction. Based on that, we find out the approximate, what we call as approximate influence of that particular region on the output. So 3 stages. First stage, take the original input, break it into small regions. Each region you perturb and see the influence or variation on the corresponding output. Then you try to, by looking at what part of the image is, or what part of that image is causing more influence on the current classifier or output, we say that this particular region is responsible for the particular topic of interest. So the idea is, this is entirely black box. What you look at is you try to select the instance of interest, perturb the data set, get the black box predictions, then weigh the new samples according to the proximity to interest instance, which is usually a linear perturbation, then do a weighted model, which is a linear model with respect to variations. Then you see what part of the original data is actually responsible for your particular decision. So the beauty of such an example is it is independent of what model you have used for your machine learning. It is black box, and also it is important to understand that this can work on explaining both correctly classified instances as well as incorrectly classified instances. So let's take a actual example here. Let's look at the second image here. So internally, it's actually a cat, but if you look at the torso of the back of the cat, it is actually looking like a dog. So the green portion is explained by line as the potential reason why it is classified or predicted as a dog, though it's actually a cat. Similarly, if you look at the last one, for example, its torso is looking more like a cat, so it predicted it as a cat, though it's actually a dog. So what line does is line uses concept of model agnostic mutation testing based approach to locally obtaining mapping of interpretation of a specific region to the target decision. So now if you have the output like this, then you can go back and change your training model. Training data can be changed, saying that I don't want to give it confusing instances which is going to cause such misclassifications. So that is the power of explainable AI. So this was like a very high level view of explainable AI with some level of detail on one particular technique like line. But this is an upcoming area, very useful for domains like insurance, healthcare, etc. And in fact, it is very much possible that in healthcare insurance models, we will not allow an AI without a good, strong, explainable model backing it. Now, going beyond explainability, we need to also understand that there are several issues with respect to AI from a fairness beyond transparency, bias, fair, unbiasedness, representative of the population. This is the requirement for all our typical AI models. So to give an example, there is a classic case study of recent Amazon HR recruitment tool powered by AI, where they had to withdraw the recruitment tool from the specific deployment for certain kinds of what we call as prediction for promotion or salary raise, etc. But the model was considered to be biased against lady employees. So naturally, such kind of a bias, which is not fair in the rule of law and also as a societal requirement, is not wise to deploy such an AI model, whether it is for recruitment or whether maybe it is for promotion or whether it is even for understanding specific patterns of diseases, etc. So you need to understand that fairness is not to be compromised when you're going and deploying AI systems because of the specific reason that we are not going to accept it without backlash or without some kind of a, breaking the rules related to compliance. So we want the fact that any generated model, which is generated from an AI model, should be based on a fair, representative, and unbiased process for collection of data, which is fed to the specific translation of the data to model. So we need to always measure that the generated model should be representative of the population without any bias. Input data may be biased, but you have to make sure that the way you convert that to the training data is by either oversampling the less represented data or by undersampling the majority classes. But it is required for us to create a fair and ethical model for creating the final AI model which will stand the test of ethics. So what exactly can we do to avoid such kind of issues with respect to bias and not falling short on ethics? We can make sure that training data is represented in proper representation of all the classes. Testing for fairness should be part of the process. Means when you're talking about feeding training data to your model for training, we should always be clear about whether there is a unfair bias against maybe an underrepresented class, or is there a specific class which is overrepresented. We need to make sure that that can be nipped in the bud by using technologies like SMORT or stratified sampling before feeding the data into the training process of AI. Then corner cases. This is very important for driverless cars. For example, let's take the example of the accident which happened with Tesla car. What happened is it went and rammed into the truck on a California highway because the truck's background was blue in color and was matching the clouds in the background. So we need to make sure that when you have corner cases, they need to be prominently picked up in the training process so that we are constantly aware of training for the corner cases so that we do not fall into the trap of, accident scenarios. Then the next point is very, very important. Constantly monitor the deployed model for bias or drift or any kind of issues which are against human judgment from ethics perspective. So as language changes and usage shifts, as biases and prejudices are discovered, the algorithm should be revisited and retrained on new data. Classic example is, I don't know whether you're aware, the Microsoft chatbot called Tay. In 24 hours time after deployment, where it was deployed to understand customer sentiments and end user sentiments of how people will react to such chatbots, it had to take it out because apparently the data it was fed to by end users was leading it to adopt a very racist inclination, which was not at all acceptable. So it could not be in a public domain and it had to withdraw. So you need to understand that it's not just about training data where you need to understand bias and following human ethics, but even after deployment of the model, you need to constantly monitor and make sure that you're not differing or you're not moving away from the deployed model's expected ethical standing. So with that, I would like to stop my talk. It was a short and a brief presentation on explainable AI and ethics.
Thank you very much, Dr. Srinivas Padmanabhuni. That was not a short, that was the extensive explainable AI and the various tools which you can use and the ethics to be followed. Thank you very much for that insight, Dr. Padmanabhuni. Now we move on to the next session, which is a panel discussion.